Okay.
Hi guys, welcome to our last day of advanced track. Thank you guys so much for coming and sticking it out with us. And yeah, so as promised in the beginning of advanced track, we are going to be doing a guided project, computer vision guided project. So yeah, stay tuned.
Yes. Again, as always, our cluster link is right over there. Our link tree is over there with the QR code to the Discord. And you will also find the link to the skeleton code on here as well. So we'll show the link for the skeleton code in a little bit, where we're going to be kind of walking you through it. However, if you want just straight to the link of some filled code, you can also just go to this cluster and you'll be able to find a link to these slides, and inside, if you go to this cluster, you'll also find a link of an example filled code. Though when we're just writing code down today, we may deviate slightly from the example code. So just kind of putting that out there. Okay, so I'll put this on for a little bit before we continue. All right. Announcements. Yep.
So for today's content, yeah, our main goal is just to walk you guys through the guided project and hopefully get a model up and running so you guys can be able to classify images in a specific data set, which we will be introducing now. Yeah, so just a general overview of the project. Your task is to train a CNN as a classifier for the CIFAR-10 data set. And how we're going to do this is that we're going to have a Jupyter notebook, and it's going to run the Conda environment for you. Yeah, and so everything should be like pretty much like set up, or yeah, actually, yeah, we're going to be using a Google Colab for the environment. And so like it should like help mitigate like any of like the setup issues that we might have. And essentially, we're just going to be walking you guys through like writing some small snippets of code, and hopefully kind of get you guys thinking about how you're able to kind of like manipulate the like documentation, as well as like any functions that we have introduced like 2 weeks ago during our backpropagation workshop. Yeah, and just for like a quick plug, here's the documentation just for like your own like learning, or if you ever get like stuck on anything, you can always read up on like the PyTorch docs. They have a lot of great information. They're very detailed, and yeah, they essentially tell you pretty much like how to use like pretty much all the functions, as well as like the many parameters they might have. Right, and then just other helpful pages that we have linked here. None of these are like necessary. They're just kind of things that like if you need help getting started, or if you just want to kind of like learn more in the future. Yeah, and so just like a quick introduction to the data set that we're going to be using. So this data set is the CIFAR-10 one, and it consists of a whole bunch of colored images split up into 10 classes. So yeah, and your job is going to be able to classify like images of any of these 10 classes, and hopefully have your model classify into the right class. And yeah, this is just kind of like a visual like diagram of like what this data set looks like. Yeah, so as you can see, like here are 10 options, like airplane, automobile, all the way down to ship and truck. Yeah, and so this is going to be what we're working with today. All right, and so for the guided project, here is the link to the skeleton of it. This is the unfilled version. So if you guys could just put this inside your browser and then open it up, and you're going to have to make a copy of the Google Colab. Then after you guys are all done with that, we're going to get started on actually coding things up.
Yes. And to show you, actually, I'll probably just click on the link. Just click on it. You'll see something like this, which is basically, you know, our little skeleton code ready to be filled in. I will zoom in a little so you can see a little bit better, like that. And what you want to do to make a copy is click on the top left-hand corner. You'll see File. Save a copy in Drive. Right, so that's the little thing you want to click. Click that. It should be creating a copy, and you click Open a new tab, and this should be the one that you're working in, because we don't want you to be editing the skeleton code. It can get a little bit messy. I don't think you have permission to edit the skeleton code anyways, but you know, just to be sure, I'm just going to put it on light, because that's usually slightly easier to see. Okay, feel free to gonna look up when you're done. It's time to do so. Oops. Got it. Okay, cool. Let's begin.
So, so just as overview of like what's going on. So this chunk of code right here is where we're importing all of the libraries that we need.
Actually, one thing before we even get started, we want to train on the GPU, right? Currently, I believe Colab will default to CPU. So what we have to do is click on runtime, as you can see over there, and then click change runtime type. And you want to make sure that GPU is selected. By default, it may select none. You want to ensure that GPU is selected. GPU is something that's a little bit more specialized. We're not going to deal with that. But yeah, we want to select GPUs. Does anyone have any idea of like why we're using GPUs instead of just CPUs? They're faster, but like, do you know why they're faster? Any ideas of why that's the case? It goes back to the idea of what are neural networks really, and what is backpropagation? How do we compute all these things? Most of these operations are matrix multiplication, matrix operations, right? And GPUs were originally designed to display video. It takes some sort of input signal and displays it onto your computer, right? And if you take CS174, you'll realize that most of computer graphics is just matrix operations. It's just linear algebra. So machine learning, because it requires a lot of matrix operations and a lot of, most importantly, parallelization, it happens to be also something that GPU is really good at, and something that's in all of our computers. That is why people have found, wait, we can just train stuff on GPUs. And that's how kind of GPUs have almost evolved to become the sort of #1 thing that people train machine learning models on nowadays. Another thing with GPU compared to CPUs is GPUs, each core is much weaker than a CPU, but there's a lot more cores. You may have heard of the most recent GPUs having like thousands of cores, whereas even the relatively good desktop GPU may just have 16 or 24 cores nowadays. And because with machine learning, you're calculating so many operations at once that can be parallelized, being able to have a bunch of cores and be able to divide tasks to a bunch of these cores makes GPUs very, very helpful. So that's why I want to use GPUs. So we'll click save. You may have to restart the runtime. It'll prompt you with some stuff. But are we all good with that? Okay, cool. Let's continue.
So so this is just us importing all the libraries we need. Yeah, like if we don't import them, you just can't use them, and nothing will work. So yeah, this part's pretty important. And then to like actually run it, you literally just press like the run button.
Or you can click on the actual cell itself when you're in text editing mode and do Shift Enter. That also helps.
Yeah. And then you can see like it's running, and then after it's done running, it will kind of just like give like a little check mark at the very left. And then so another thing that we also like to do is just kind of like have like a quick like check. So like sometimes you might not have GPU available, and if that's the case, we still need to run it on something, and so therefore we will default to CPU.
Yes.
Yeah, this is not really a problem with like Google Colab, but however, if you do run it on like your own machine or something, this little chunk or like this check is very necessary.
Yes. It's kind of like a convention at this point for us to set the variable device into torch device, whatever, if you're running a CPU or GPU. Because one thing about PyTorch compared to something like TensorFlow is it requires you to be quite explicit about this tensor is on the GPU or this tensor is on the CPU. And you want to make sure that everything is on the GPU at all times. So having this kind of device here is pretty important because as you will see later, when we're writing our training code, sometimes we have to explicitly put our model, for example, to the GPU. We have to explicitly put our like inputs and labels to the GPU, for example, for this to work. Does that make sense? Okay, cool.
So this is just our basic setup, just like our environmental setup. And so now we can actually get into our first step, which is data processing. Right? We need to be able to like grab the data somehow, or else we're not going to actually be able to train our model on anything. Yeah. And so if you look at this cell right over here, we have already pulled out the data set for you guys. And so essentially we're going to have two data sets. So first one's going to be our train data set, right? And our second one is going to be our test data set. And if you notice, like the only difference is that the test data set is going to have an extra parameter called train, right? And what this is going to do is it's going to just tell our computer like, no, like we're not going to train on this data set. This data set is purely for testing purposes only. So so this one is just us being able to pull out the CIFAR-10 data set from Torch Vision or from Torch. And so this is just kind of like our general setup. Yeah, and so now that we have our data, like now that we were able to like fetch our data, we need to now figure out a way to load our data into the model. And so but this is why we have our train and our test loaders. And so that's what we're going to do.
Sure.
Yeah, we can take like maybe like a quick like 5 minutes to just kind of like play around with this really quickly, and then we'll go over like how to do it yourself. Yeah, but just for some hints, you can look at this workshop right over here, workshop 5, or you can also look at the PyTorch documentation right over here.
The PyTorch documentation, compared to a lot of other machine learning library documentations, is awesome. Like one of the things you've probably been taught in 31, 32 is like, read the documentation. And in the case of PyTorch, that really helps. Because a lot of times you're like, wait, I don't know what options, this particular, function takes, or this particular class takes. PyTorch usually explains it pretty well. And that is why with PyTorch, a lot of times you don't want to just look up what does this do on Stack Overflow, but the documentation itself is very well written. And they also link you directly to like the source code and stuff like that, which is actually quite readable for what PyTorch is. So that's something that we definitely recommend. Okay. I'll pause a little bit. Okay. Let's come back, even if you haven't figure this out. We do want to not keep you for too long, but the syntax for defining training and testing loader is as follows.
So over here, we're going to use a predefined function in the Torch library, and we can call it by doing torch.data loader.
Yeah.
And as you can see over here, it kind of like already like prompts you here, right? And then now that we have our data loader, we now need to figure out like ways that we're able to kind of like manipulate it, right? And so as you can see over here, it gives us like the list of parameters that we can play with. It might seem like kind of intimidating because it's a lot of parameters, but just note that you only need like 3 of them, or like you only need like 2 of them, but we'll go over like 3. So the first thing we need to pass in, as you can see here, is like the data set itself, right? And so you can see we have already defined that here with our trained data set, right? And so we can just pass that in, trained data set, pass that in into our trained data loader, right? And so that's going to be our first parameter. And then the second thing that we do need to specify is our batch size, right? Because we do want to train in batches. We don't want to train everything all at once. And just for the sake of this workshop, we're going to set it to 128. Then another thing that we also like to do is that we like to have like the shuffle parameter, right? Because it's good to just kind of like randomize your data. And so all you have to do is just do like shuffle, and you can set that equal to true. So this is going to be what we do for our training loader. And so now that we have that, we just need to do the same thing for our test loader. Yeah. So we're going to use the same function that we used for our train loader. But this time, instead of passing in our training data set, we're going to pass in our testing data set, which we have already specified right here.
Yeah. And just to kind of clarify, a lot of times it's a bit confusing. It's like, okay, so why do we need a data set and then we have a loader? Why can't we just load in our data sets? So what the data sets object actually does is it actually contains the raw data of like what CIFAR-10 is. And the raw data in this case will be like some sort of like, like raw bits and bytes. And basically what it tells PyTorch is how do we read those bits and bytes, right? Because like these data sets typically don't just come in like a bunch of JPEGs, because if you have like 200,000 JPEGs in a folder, that will probably crash your file explorer, right? Trust me, I've tried. Actually, PyTorch does actually have a specific type of data sets of classical image folder that actually handles these sort of things. But again, that's more advanced. You can read the documentation to find out more. But what the data set does is it basically says, if we want to retrieve one image, what do we do, right? And by having this data set that basically tells us and contains all these information, what the data loader does is it takes this data set and it says, okay, let's compartmentalize all of this into nice little chunks of, like, in this case, 128 is our batch size, one nice compartmentalized bits that we can just very easily just, do a for loop over to do our training. So that's what's happening here. That's why we have 2 separate things. Is here's how we actually read the data set. Here's how we then very nice. You can just iterate through the whole data set. Some people just deal with this directly if they want a lot of control, but having a data loader is pretty nice. Does that make sense? Okay.
Yeah, and so after we get our test data set in, we're going to do the same thing with our batch size, and we want to keep it pretty much the same. So we have it set to, and then we can also shuffle this data set as well.
Yes.
So are train loader and test loader some kinds of lists then?
They are just a class inside them. I believe it's .data and then .labels. They have like the corresponding like image and then labels that's in there. And one thing you may notice here is transform, right? Like what this transform keyword says is basically as you try to retrieve one of the entries, do this to it. And what torch vision.transform.toTensor does is technically with this transform, we can do more complicated things. Like you can actually specify a whole like transform object that can do, maybe scale the images to 0 and 1, and then, do this and then do that. There's a bunch of data pre-processing techniques you can do. But torch vision.transform.toTensor is the simplest one that basically says, for any sort of usually NumPy array, take that in, turn it into a PyTorch tensor, and usually also scale it to between 0 and 1, because usually images inputs are 0 to 255. And then the one more thing it does is remember, in PyTorch, instead of height width channel, it's channel height width. So toTensor also does that for you. Because it's part of the Torch Vision class. Torch Vision, they have this whole convention with channel height width and stuff like that. So that's what this transform keyword does.
So now that we have successfully loaded our data using these functions, all we have to do is just run it to get everything that we need. And then another thing that we have right here is just like a nice like chunk of code that's able to visualize like a sample of our data from our training loader. Just kind of like a quick like sanity check to be like, am I like actually like doing things correctly?
Yeah, if you see here the image.permute120, that's changing our channel height width PyTorch image back to the height width channel normal image. Because again, every single other package expects height width channel, but PyTorch likes channel height width. Because if you think about what happens in convolutions, channel, and you have input channel, output channel, having those two things in the very front is kind of nice for a lot of matrix operations because you don't have to reshape a bunch of things. So it's nicer in the context of neural networks, but when we're displaying things, the image.permute is kind of important because of this thing that PyTorch does with putting channel at the beginning.
And so with this one, we can just quickly run it, and then it should give us like an image. Yeah, so this one's like a car, this one's like a bird. Yeah, so it's just kind of like a quick sanity check, like, oh, is my data actually being loaded? And then so now that we've finished setting up the data and processing it, our next task would be to actually build the model to work with the data that we have just loaded in to train it and classify it, and hopefully build like a successful like image classifier.
Yeah, and okay. And just as a little hints to like how do you even begin, what we want to do is we want to subclass the nn.module commands. And if you're wondering where n comes from, it's just torch.nn, but we import the nn directly. And what the nn.module does, if you remember from last time, is this basically thing that allows you to be able to check parameters, look at all your parameters and be like, let's do, backpropagation stuff to it. It's basically this kind of all-encompassing thing if you want to write, in this case, custom models or even just custom layers if you want. So like, if you're in the future, you may be writing more complex code with PyTorch, where maybe you're defining, say, custom layers. You will also be using an nn module, and honestly, a lot of really complex PyTorch models is just a bunch of nn modules nested within each other, right? So we basically want to subclass an nn module, and if you remember how to do so, do actual like initializations in Python. I don't think you even need, like some people will do like CNN self that. You can, you don't have to, you can just do that, and that basically is like your super, you're like, I'm gonna subclass this thing. Syntax. So I'll also add this here, self and x. So basically you will have, self is kind of like the this, I think, in C++. And x will be your input. And usually the for function has all expects, but technically your for function can take any number of things depending on your model. But again, I'll leave you to it for like 2 to 3 minutes while I kind of slowly type out some code on screen. Maybe I'll like give some pointers of like, you can try to define convolutional layers like self.conv1, for example. like that, and you have something like your input channel, your output channel. Again, we'll actually type this out. I'm just saying, your kernel size, your stride, and your padding. So that's kind of what we're dealing with here. I'll give you a little time to kind of try to figure this out yourself. But again, we're pretty tight on time today, so I'm going to come back in probably just 3 to 4 minutes. So have a little look at Conf2D documentation for on PyTorch website. I'll actually bring it up honestly, because why not? So PyTorch Conf2D right here. And you'll see what I mean by the documentation is pretty good, because it actually tells you like a lot of things, right? It tells you what the first argument is, in channels, out channels, your kernel size, your stride, your padding, and then there are some other more like advanced convolutional stuff like groups. And bias just says, is there bias term at the very end? Because sometimes you don't actually want a bias. It actually tells you what the operation is mathematically, and you can actually figure out if you want a certain output, what is the way to calculate. It looks very complicated, but if you work through the math, it does make sense. What is the way to calculate the output size? So that's something you can look at. So yeah, I think this documentation is quite awesome. So I'm going to share it here. But yeah, I'll let you kind of just go at it for like 2 to 3 minutes, and I'll come back. Let's pause this thing. Record actually. Does anyone remember what stride is? In this case, and does anyone remember what a convolution is? We covered this in workshop 3, but it's been a few weeks.
Let's try to like a window.
That's kernel size, right? So that's the width of your kernel.
How many pixels or how many steps
you take at every. That's exactly correct. And we can use stride to be able to do things like downsampling, for example. So that will be pretty helpful. Yeah. So padding, and then we have some other really fun ones like dilation. Dilation is like, instead of doing like a 3x3 in here, what if we spread it out? So that's the thing you can do. Groups is like, you can do this in groups and like reduce number of parameters. It's the whole thing. You can definitely look into these basically things people have proposed to convolution little layers that make it a little bit more flexible. So yeah. Okay. I'm going to just come back and just try to define a network for us. So one of the really important things, is it this one? Is this one? Okay. So one of the very important things with defining a PyTorch model is knowing exactly what the size of your current input is, right? Because we start out with CIFAR-10. So I want to just kind of write here, CIFAR-10 is 32 by 32, right? Or it's going to be 3 by 32 by 32 because it's a color image. You want to really keep track of this number of like, is it 32 by 32? Like maybe like every time because every time you perform convolution, what happens is this, right? And let's say we set an input channel of 3 and an output channel of, let's say, 32, right? So why not? And let's set a kernel size of 3 because the kernel size of 3 is generally pretty common. Let's do 5, why not? And we do like a stride of 2, right? Then what we want is the whole point of having a stride of 2 is so that we're downsampling the image from 32 to 32 to 16 by 16. However, if we don't specify a padding, what happens is, well, first of all, do you remember what happens if we don't have padding? Let's say we have a 32 by 32 image and we're convoluting it with a 3 by 3 kernel. What happens if we don't have padding?
Yes, it will have a different shape than our input.
Yes, that is exactly correct. It will have almost like an unexpected shape because if you think about it, because we have a 3 by 3 kernel that's not a 1 by 1 size, it will kind of reach the end. If we don't have padding, we'll just stop. So if we have a 3 by 3 kernel over a 32 by 32 image, for example, I believe the output is actually 31 by 31. And yes, that's fine. If we keep track of our sizes of our input and outputs very carefully, we can probably make that work. But that's kind of a weird number. We want like a nice 32 to 16 to 8 sort of like downsampling process. So that's why I say to be very, very careful about these things. I believe there is a type of padding called valid that you can do that does this automatically for you. But I believe that should work actually. Let me just check to make sure that works. Okay, yeah. So that doesn't work. Okay, so let's do something a little bit simpler. So we can go through all the math to do like the whole stride thing. Like we can look at this and be like, okay, what's the stride? What's supposed to be the actual thing? Or we can just kind of do what you remember as keeping the size. So in this case, I want to set a padding of 1. And the reason for doing so is because if you imagine we're doing a convolution, actually, while we're at it, let's go down to this, right? We want our input is 32 by 32. We have padding. We want some padding such that our output is 16. So if I do like a 32 by 32, I have a kernel size of 3. So 3 minus 1, that's 2. Dilation defaults to 1. So we have 30. You may have to do this in the future, by the way. 32, we have a minus 2 situation. The kernel size, minus 1. So 30 minus 2 minus 1, that's 29. And we have 29 divided by the stride, which, and we're taking the floor of it, which actually works out to be 14, I believe. So to make sure our output is like, we need a padding of 1. Because if you think, oh, no, we need a padding of 2 actually. So what we can do is actually to test that out, we can go back to our development code, kernel size of 3, stride 2, padding of 2. What we can do, if you are just unsure, you can literally just do, well, x equals to self.conv1 of x, just print a shape of x, right? So you can initialize this module. I'll just kind of pass through the model, you know, create an instance of this model. I'll just say, okay, let's just pass it through CNN, torch. Let's just create a random tensor in torch. Let's do batch 128, 3, 64, 32, 32. And see what that gives us. 17, 17. So actually we have too much padding. But we do padding 1, that should work just fine. You can see we put in an input 32 by 32, we get out an output of 16 by 16. Right? So that actually shows you, if you want to be really sure that the shape of your stuff is correct, this is how you can do it. Just like quickly initialize a little version of this model and just make sure that everything's correct. So to be kind of rigorous of like making sure we know exactly what the size of everything is, let's just kind of write out what's happening, right? We're going from a channel size of 3 to 32, and we're downsampling to half the size of 4. So we went from 3 by 32 to 32 by 16 by 16. Does that make sense what's happening here? Okay, so let's actually, why not let's just do that a few more times. Oh, I just accidentally ran it, but let's just do that a few more times, right? Let's do that 2 more times, shall we? We have conv 2, conv 3. What should, okay, so we have in and we have out again. What should this in channel be? If we know that the output channel of the previous layer is 32.
32.
Should be 32, right? Because we need the channel numbers to match up. If we're just planning to apply this right after another. So we have 32 here. And again, here is where you can make a decision of like, what do you want your inputs and outputs to be? In this case, I want to actually scale up my output channel. Because there is this kind of heuristic in machine learning, where if you have a sort of 16 by 16, this will be 8 by 8 actually, I believe. Channel 64. The heuristic, the idea is that as we're downsampling the image with stride, we're starting to capture more and more global information. Because if you remember, the receptive field of each neuron becomes bigger and bigger. Each neuron in these output feature maps is seeing more of the image as we're downsampling. And because we're almost like downscaling the image and we're kind of quote unquote losing the sort of beginning spatial information, every neuron starting to look at more global features. We want to capture more global features. So there's this kind of heuristic of the deeper we go with layers, typically we will actually add more channels at the end. Does that make sense? What's happening? Yes.
So basically you're analyzing images like in different ways.
Yes.
And then you're gonna put that all together to be able to create a model.
That's correct. Like you can think here, we have 64 feature maps that are all 8 by 8 in size. Each of these 64 feature maps may be capturing slightly different things about the image. Does that make sense? Okay. So live coding is stressful, but Let's end it with we can keep going with going all the way to 128, but I don't want to because it may take a little bit, right? We can do 64 kernel size of 3, stride of 2, padding of 1. That gets us all the way down to 64 by 8 by 8 to what's our output size in this case? Yeah, yes. 64 by 64 by 64. 64 by, well, we're downsampling by a factor of 2. Where we have channel, height, and width. 64 by 4 by 4, right? Does that make sense why it's 64 by 4 by 4 in this case? Okay. I'm hoping this makes sense so far. Is everyone following of like why we're doing these sort of layers? Sort of, yeah. So kind of just to reiterate, we're basically with the stride of 2 because we're moving by every time we're moving our filter by a step of 2 instead of 1 every time. We're effectively basically downsampling the image because we're kind of doing the skip, and hence there will be a smaller output feature map. And we're using padding was one to make sure that the size really nicely matches up. And we're basically slowly increasing the channel size in front to basically kind of go from a 3 by 32 by 32 image to these things that basically start to actually capture global information. And that's what we're doing here, right? And actually, while we're at it, let's not do a stride for this one. Let's keep it 64 by 8 by 8 because I want to show you another thing. And again, just to make sure while we're at it, might as well make sure we apply all these things and do a quick little shape sanity check. Is it actually 64 by 8 by 8 there? Let's see. Yes, that's correct. 64 by 8 by 8. Our size actually does match. So that's great. Because I want to show you another thing. Does anyone remember max pooling and what that's doing? Anyone who has forgotten what that is, which is fine because it's honestly been a few weeks ago.
That's just a kind of a reversal of like convolution.
That's transpose convolution. That's when you get bigger, right? Well, max pooling is basically another way to downsample the image. That basically says, for example, if you have a max pooling, I believe is in the max.
The max value of it.
Yeah. So to stride equals 2 t stride. So what that's actually doing is basically we're looking at these 2 by 2 windows, right? And we're saying for every 2 by 2 window, take the largest value. Move 2 over. For every 2 by 2 value, take the largest window. So we're almost basically downsampling the image again, but this time we're doing it in a way that we like to call invariance. Some people prefer doing this. Some people prefer just using stride. I'm doing both, so I can kind of show you that you can definitely do both of these things as well. So we go from 64 by 8 by 8, 64 by 4 by 4. Does it make sense what's happening here so far? Okay, cool. And then we can have something like, and then now let's say these are all of our convolution layers, and we want to output these to fully connected layers. What should we do? We have 64 of these 4 by 4 feature maps. What can we do with that? What should we do so we can feed it then into a fully connected layer?
To make it into a vector.
To stretch it out into a vector, right? Or in other words, to flatten these feature maps. And the way to do it is actually, we have really nicely, PyTorch gives us a tool just to do that and that flatten, right? So in this case, we are actually going from, I'm going to add the B in the front, which actually stands for batch size, because that's kind of important. We're going from the batch size times 64 times 4 by 4 to, because we're flattening it all out, batch size times 64 times 4 times 4. Because for every single entry in the batch, we're stretching out all these feature maps into a vector. And I'm honestly not just not going to calculate it because we can just leave the 64 times 4 times 4 the way it is. And we can add the linear layers, right? So linear 1, fully connected layers. Actually, linear is a bit much. Let's do FC. Fully connected. Our number of inputs, 64 by 4 by 4. And let's say we want a hidden layer of 128. And we can define another fully connected layer that outputs to 10. Why are we outputting to 10? Like this will be our output. Why are we doing 10?
There are 10 categories.
Because there are 10 categories. There are 10 classes for CIFAR-10, as you may have imagined. So that's what's happening here. And again, this may seem a little bit tedious, but I want to be very sure I know exactly what the dimensions of my tensors are. B by 128. At the very end, B by 128 becomes B by 10. So we have the cloud predictions for every single image on batch. Okay.
What does DX stand for?
Oh, BX. It's actually just because it's B times.
Oh,
So B in this case is the batch size. So B is the batch size. So the reason why I added B here, not before, is because before the batch size just stays the same. But up to this point, I want to be very clear that when we're flattening, we're leaving the batch dimension intact, right? Every single operation here is done like separately to every single one of these things. Does that make sense? Okay, so let's apply these layers, shall we? Self.pull, X, self.flatten, X, self.fc1, X, and then at the very end, X equals to self.fc2. That gets us an output. And we're done, right? We should be done, right? We've done all the convolutions, we've done all the layers. Actually, we're missing something. We're missing something here that's pretty important that we really stress in the beginning. That we spend a lot of time talking about actually kind of in the beginning. I'm wondering if you can see that we're missing. Hence, the word starts with an A.
Activation.
Our activation function. That's exactly correct. We're missing our activation function, right? Even like with self-fully extended 1 and fully extended 2, these two basically just become one big linear transformation because that's how linear transformations are. You can make the argument that, oh, well, but the convolutions themselves, that's non-linear, so it's fine. But experimentally, we show that activation functions are actually very, very important. And it is very useful to have activation functions in that regard. By the way, I believe the filled-in version of the code is actually not correct. So please try to refer to this as much as possible. I'll try to update the code in a little bit. But if you remember up here, we imported torch.in in the functional, right? Which is basically an interface that has all these operations, but in a functional way. So basically, we can just do things like add a ReLU around this. And because ReLU doesn't have any trainable parameters, we can do stuff like this, right? ReLU just says chop off everything that's negative and make it 0, right? And it adds non-linearity. But if we do this, what we basically have is we're adding our activation function. Does it make sense how this is adding our activation function? Does that make sense here? Okay. I do want to make sure that this is okay. Yes.
Throwing the results of the comp into a function.
Into function, specifically ReLU, right? Actually, while I'm at it, let's add another layer again. Like sometimes with designing. Oh yeah. Actually, before we do that, I actually did C, so it should be X. I'm not going to add a ReLU in the output layer. Why am I doing that? I'm not adding a ReLU. It's just I'm leaving it the way it is. Why? Again, this is just kind of like a neural network design heuristic. Typically, the output activation is not the same as your hidden activation. With the older neural networks, it's just sigmoid all the way through, and you will be fine. But what we want to do is we want to keep the outputs what we call raw, aka the raw scores of every single class. So you may, for example, for the 10 classes, one of them may be -5, one of them may be 3, right? The 3 obviously seems a lot more important than a -5 one. So usually what we would actually do is we would actually apply a softmax function like that. And if you don't know what softmax does, I can show you what that is. So softmax it looks like this, right? It's this equation that basically changes, in short, changes your output scores into a nice probability distribution that your optimizer can understand. But we're not doing that because nowadays, optimizers typically have the application of softmax built in, right? And it'll be clear in a little bit what I mean by that. And because they have it built in, because what our loss function is, we actually apply a natural log function to our outputs. And because we're applying a natural log function to our outputs, and what softmax does is it does e to the power of something, these two statements actually cancel out. So there's actually a way for you to mathematically simplify the application of softmax and then the activation and then the loss function together, right? So that is why, because there's a way to mathematically simplify it, instead of doing the e to the power of whatever and then getting rid of it by using a natural log, what our loss function says is basically just give me the raw scores. I'll figure out the math myself, because that actually allows us to have cases that are more numerically stable. Because, for example, what happens when you have natural log of 0?
It's undefined.
It's undefined. It's negative infinity, right? If you look at the plot of natural log, it's like it just kind of does like this, and at 0, it just shoots off to negative infinity. That may happen with really odd results if we have something numerically unstable. And again, this may all seem really confusing, but like I'm trying to justify why we're not putting a sort of activation function at the very end with at least more modern machine learning frameworks. Does sort of make sense what's happening here? Okay. Just to demonstrate, I'm going to add an additional thing in the second layer. Again, this is not the greatest, design convention, but I just want to show you how these layers work. So we can add something called batch norm, right? Batch norm 2D, like that. And we want to put in the output channel of that. And I actually want to add batch norm right after. Usually you would add it at the end of every layer, but I'm just going to add it here. And does anyone remember what batch normalization actually does?
Doesn't it just adjust like the mean, so it's like 1 in the variance, so it's
0 variance is 1. Yeah. So it basically normalizes the magnitude of your hidden outputs so that you don't have problems with just like gradient explosion, where the outputs of your hidden layers gets bigger and bigger and bigger and bigger, and your gradient gets huge. And then when you do a gradient descent step, it just becomes undefined, like your model weights, or the opposite, which is gradient vanishing, where your hidden outputs become smaller and smaller and smaller and smaller. And then when you do gradient descent step, it's like basically 0, and you have done absolutely nothing. What batch norm does is basically says, let's basically make your model more robust by making sure the magnitude and the mean and the variance of your hidden outputs are roughly the same, right? So actually, while we're at it, I might as well just add it to every single layer. So batch norm 1, again, all it does is it just normalizes your layer across the batch dimension. And the reason why I'm putting 32 is because we're doing this operation across the entire channel, right? With normal batch normalization, what you will actually do is you do this on every single feature on the feature map, but that's problematic for batch normalization because, for CNNs, because the whole point of CNNs is that the relative values of your feature maps actually matter. So if you just normalize all of them independently, you have lost that relative information. Hence, we actually do this on the entire channel dimensions. I just want to correct this because I wasn't being very precise the last time I mentioned batch normalization, but I'm just going to put this in because this is something that will help with our performance. And like one of the things, when you just start using batch norm and you add it to a model that maybe didn't have it before, I'd also add another one. Actually, I'll just leave it like this. If you add it to a model that didn't have it before, you may not notice a big improvement in performance. But what batch norm does is it actually makes your model more robust. Like, for example, if you have a really large learning rate, or like your model weights becomes really large, it's able to basically say, okay, I can control that a little bit by making sure the output activations are kind of a bit more controlled, right? So that is what batch norm does. It makes your training usually faster because you can be a little bit more liberal with the initial hyperparameters that you choose. because it makes your model more easier to train, if you will. And we get to really, really deep models, like models with hundreds of layers, which is kind of the case with a lot of modern convolutional neural networks. Batch normalization or some variants of normalization within every single hidden activation layer becomes very important because it's really hard to control the magnitude of your hidden activations when you have that many layers. In this case, we can definitely do without batch normalization, we'll still be fine. But batch normalization is really nice because it allows us to do this. Does that make sense? What's happening? Yeah. And while we're at it, we might as well just like make sure our input and output shapes are correct, right? We put in non-type objects testing. Oh, that's tricky. Oh, because I think I didn't do that. Cool. So we pass in that matches, right? If we pass in a sort of random image that's 128 in batch size and our 3 by 32 by 32 as expected, we get an output size of 128 by 10. That seems like that's what we want. So we have just confirmed that our model is indeed working, at least in terms of, in this case, the dimensions of everything. And we can initialize our model by just calling the class, right? Now, in the future, when you're making your own machine learning models, you can actually define things like input dimension and output dimension, and it just depends on how you want people to initialize your model. In this case, we know exactly where our input and output dimensions are, so we're not actually accepting any arguments for the initialization function, but you can obviously put in stuff like that, right? You can, for example, even specify like a list of filter sizes you want your convolutions to be, and you'll perhaps write some for loops in here that will be able to handle that. But in this case, we're not actually accepting any arguments, so we're doing just that. It's a little bit because, oh, by the way, you can see that's a little sort of, summary of our model, right? So this, and another thing, what this model.to device does is basically just puts the weights of the model and it puts it on the GPU. Because when we're doing forward propagation, backwards propagation to calculate gradients and whatnot, to actually train the model, in order for everything to be calculated with the GPU, every tensor that we interact with has to be on the GPU. Therefore, we're putting the model to the GPU, in this case, just device. Does that make sense? Okay. And I'm going to cover loss function and optimizer right before we take a short little break. So here is where the whole thing I was rambling about how we don't have an output activation start to make sense. So what you have been taught, or like in the past, you may have heard of something called mean squared error. Has anyone heard of that? Mean squared error, right? And like if you think about it, it's like, what does that mean? Well, you take the actual labels and you take your actual labels, which is the one hot. Does anyone remember what one hot encoding means? If you don't, I want to remind you the output dimensions of this model is like for every single image is a 10-dimensional vector, right? Each dimension corresponds to the probability that the image belongs to the class. So what the label is, to turn in the label that this belongs to class 6, right? The label is just 6. To be able to translate it to what the same thing that the model is working with, sometimes people want to do one hot encoding, which is basically say 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. Because we know the 6th entry, which corresponds to the 6th thing, has to be 1. And it will be similar for all the other classes. Does that make sense? Yeah. I believe the loss function does like just handle that for us, which is kind of nice. So we can do that with a mean square loss between the one hot encoded vector and the output. But today we'll be using something that's actually much more common for classification models. That is torch.nn.cross entropy loss. And I want to show you what PyTorch has to say about this thing. And again, why? So this is the function of what it's doing. You may be like, what? Well, I'm going to show you real quickly. That looks familiar, doesn't it? That's just softmax, right? This is just softmax. It's basically taking a log all of that softmax, and it's saying we want to make sure the label of the correct class, or like basically in this case, let's say the correct class is 5, right? We're only looking at entry 5 of our output sort of probability distribution. We want that probability to be as high as possible. That's all cross entropy is. We want the probability of the correct output class to be as high as possible. And maybe like, wait, why don't we want the incorrect classes to be also as low as possible? Like, why do we only care about the correct class? And that lies in what softmax is actually doing. Softmax basically is affected by every single entry in your output. For example, if your output is 0.5, 0.6, and 0.5, right? What softmax they do is like, wait, 0.5 and 0.6 are pretty similar. So we convert them into probability distributions. Maybe it will be like 20%, 60%, maybe it'll be like 30%, 40%, 30%, right? So 0.3, 0.4, 0.3. Because remember, the probability distribution is to add up to 1, right? However, if let's say your output is not 0.5, 0.6, and 0.5, it's something like 0.5, 1.5. Softmax will go, because it's doing this whole like normalization process across every single, like by summing everything together, it basically goes, wait, that 1 is really high, right? So when we are converting into a probability distribution, it would be something perhaps like 0.2, 0.6, 0.2. So because every single output entry is affected by every single other output entry, by trying to maximize the correct output, the probability of the correct output entry, we're inherently trying to minimize the probability of the incorrect output entries. Does that make sense? What's happening? Like just heuristically, like when you take an actual machine learning class, you will be doing math on this stuff, right? Like at some point we do have to kind of just not shy away and just do math. But that's kind of on a very high level what's going on. And we call this, we have many terms for this, but this is called maximum likelihood estimation, which is we're trying to maximize the likelihood of the correct class, hence maximum likelihood estimation. And if you notice here, it says input logits, right? What logits basically refers to is just a fancy term for outputs without any activation. That's all it says, logits. I don't know why it's called that. There's probably an etymology for like why it's called logits, but that's what logits means. It's just output without activations. So if you're using some sort of PyTorch loss function and you see logits, that means don't use an activation function on your very last layer. Does that make sense? Okay. So we just initialize that. And lastly, let's run this just to make sure nothing weird is going on. Cool. I'll just just to end this. Yeah. And lastly, we're going to initialize our optimizer. Did we import opt-in? We didn't. So torch.optin the atom. We're going to use atom instead of stochastic gradient descent because it actually it basically keeps track of running mean of all your gradients and the magnitudes of them, and it basically tries to dynamically normalize and scale every single dimension of your gradient and basically steer your gradients in a smooth direction, but also in a way, for example, if you made a really large step, let's say in dimension 6 of your 100 parameter model, something like that, if you made a really large step in that direction with your gradient descent, it basically says, okay, we just made a really large step in that direction. Let's make sure our next step in that direction isn't as big. So that's basically in like what the adaptive part of atom is doing. You can look at the formula of what it actually is, but yes.
Was that the gradient descent does make sure that when you take like a one big step, the next one won't be as big, or does the atom model here do that?
Oh, so atom is an optimizer. What an optimizer does is it takes your gradient and says, what do we do with that gradient? Gradient doesn't just says, subtract it, maybe multiply by a learning rate. But atom basically says, let's do a little bit more with that. Let's sort of keep a running mean of gradients, make sure that everything's normalized. So it's basically a fancier version of gradient descent. That's what I'm saying. Does that make sense? Yeah.
What atom doing is similar to stochastic gradient descent?
It is basically doing the exact same thing, but with like extra fancy stuff added to it to make the optimization a little bit better.
So it's better than?
It's better. It's easier to initialize because with stochastic gradient descent, you have to be a bit more careful with it. Generally, if you think back to ImageNet, which is like the big like 1,000 class classification, you realize every single winner used stochastic gradient descent with Nesterov momentum, because there is the idea that if we use momentum in stochastic gradient descent, which is basically saying if we were going down this hill already and like we reach some sort of bottoming point, keep going for a little bit because we're keeping track of a moving average of gradients. One heuristic you can think of as like why they use stochastic gradient descent with momentum, most importantly, and specifically unnormalized momentum is because in order for a momentum thing to converge at some point, the minimum has to be very shallow, right? Because if the minimum is really sharp, it just kind of overshoots the minimum. So by using stochastic gradient descent with momentum, it actually finds a really shallow minimum. By doing so, because it finds a really shallow minimum, the sort of minimum advice, aka where the model ends up in the end, is more generalized, and usually that means better. But that usually requires a lot more finer tuning with like trying to schedule the learning rates so it's like correct at the right points, which is a more advanced concept. And most people with trickier tasks, like for example, training, let's say a diffusion model for image generation, for example, people just use Atom because Atom is just, you have to worry less about it. And when you're training like 100 million, billion parameter models, you really don't have the time to do like, I'm going to try to train this twice, change the hyperparameters of this stochastic gradient descent and see what happens. You only have one chance to train it. And we only have one chance to train it. People typically use Atom because it just does a lot of that for you. Does that make sense? It's for classification, it's usually not as good, but it's just less worry. It's just more worry-free. So what a parameter needs, again, you can reference last week's slide if you want more info on this. But what our parameter needs is model.parameters, right? Because it needs to know which parameters it's actually doing the gradient descent on. And then we're going to set an initial learning. I'm going to do like 0.003. So it has shown to be not bad, like that. Weight decay. We cover weight decay or like regularization here? I don't think we have. Okay, so all weight decay does is it basically it tries to add an additional penalty term that says, okay, let's make sure the magnitude of all of our weights together doesn't get too big. In gradient terms, all it does is just every time we do a gradient descent, the gradient we subtract it by a tiny bit of the weights itself. And the reason we're doing this is because machine learning scientists, they have found that generally models with smaller magnitudes of weights, aka the actual values of these weights are smaller, tend to generalize better because they tend to be simpler, right? We want to avoid overfitting. So to avoid overfitting, we can do regularization techniques, specifically weight decay like this, so that what happens is our model doesn't overfit nearly as much. So that's what this does. I'm setting it to a very small number, so it doesn't matter too much. But yeah. Okay, I need a break, honestly, a little bit because I've been speaking for the past like few minutes. So like, let's take a 3 to 4 minute break, and I'll come back and basically show you guys how to write your training function, your testing function, and then we can try to train a model together. Okay. Again, go on a little break. And again, you can start messing around. Sorry, what's your name?
Anthony.
Yeah, right, Anthony. So Anthony just asked, like, what happens when you get the error one of mat shapes can be multiplied? That error usually happens in one of the fully connected layers, because remember, in fully connected layers, it's just matrix multiplications, right? So usually that basically means this is wrong. Like at somewhere here, you have messed up the size, tracking the size, and the size at the very end you have tracked is probably wrong. I can take a look at it. Try to run it and try to just make sure it actually is able to run properly. I always like to, as I said, we already initialized one of these models, but I like to just initialize a version of this model. Sorry, I'll just sanity check. And just like to pass forge.rand, which just means we're creating a random tensor of a certain size. You can do a dot shape at the end to kind of check your output and make sure it's the correct shape. So just to make sure it's the correct shape. I can take a look. Well, actually, before that, paused. We have been unpaused, but all I did just now was I just switched the order of pool and match norm 3. Doesn't really matter. It's just I wanted to. And I was talking about how like if you're having some size mismatch errors, notice that I got rid of the very last stride argument here. So the stride is 1 because I want to show that you can also downsample with pooling here, right? So and then with sanity checks at the very end, you can actually delete your sanity check object just so that it's not taking up memory. That's all I covered. So let's continue and look at train one epoch. Does anyone remember what epoch means? A lot of terms in AI, but it's one of them.
Basically going through every batch once.
Yes, that's correct. We're basically looping through an entire batch once, right? So yeah, that's basically what we're doing. And however, there's one thing we gotta do before starting training. And we kind of cover this, but model.train. And the reason why we do this is actually back in batch norm. So if you think about it, batch norm during your actually like training, it tries to normalize your data in the batch dimension, right? However, when you're testing, it becomes an issue. What if you're only testing one data point, right? If you're just putting in a data size of like, batch size of 1, it can't do batch norm anymore because it does this across the entire batch. So when that's the case, what should we do? Well, the idea is this: as we are training, we want to keep a running mean and running variance of our input data. So when we evaluate this on any arbitrary batch size, we use the running mean and running variance. Does that make sense? So we have the freedom of like being able to test at any batch size at the very end. And the way we indicate to the model that we're training right now versus we're actually doing evaluations right now is with right here, model.train and model.eval, which you'll see we use in the test function in a little bit. But that's basically what we're doing. Does that make sense? Okay. We are running a little bit late, so I'll kind of just speed run through this. But basically, for I bash in an enumerate train loader, that just loops through the entire train loader. Actually, I'm going to add another argument here. Very top, import from tqdm.notebook, import tqdm. All that does is it's just a progress bar that allows us to see how much we have trained. So when I do this here, tqdm, I'm basically able to say, okay, I can see my current training progress. Actually, let's see. Like that. We have inputs and we have labels equals to batch, right? Because batch in this case is an object that's just a tuple, or in the case of pair of objects that contains our inputs and our labels. And we want to do inputs to device because we want to put our inputs and labels onto the GPU, right? That's very important because if you don't do that, you actually get an error, which is like, wait, these two tenders are in different devices. That's an error. Yes.
Go back up to.
Yeah. So tqdm.notebook and import tqdm. So tqdm, I believe, is like Greek or something for the word progress, and it basically just gives you a progress bar as you're training, so you can make sure that it's actually working. And usually, if you're doing terminal, like if you're doing this in the terminal, you're writing code for terminal, you will get rid of the .notebook. But tqdm.notebook basically just makes the progress bar look a little bit nicer just for Jupyter notebooks like this. So it's a little potent thing. Basically, if you look into it, it's just JavaScript, which you will know more in CS35L. Anyway, so it doesn't make sense what's happening currently. Okay, so let's get our outputs, right? Our outputs, we can pass our inputs through the model, get our outputs that way. Is everything good so far? Okay. And with our outputs, we can calculate our loss, right? Again, our criterion was divided up here. And we put on our very first arguments, the outputs, and our very last second argument, labels. Like that. Criterion, outputs, labels. And just as a heads up, if you're using TensorFlow, these two are flipped. It's just convention. I've gotten screwed over like that multiple times before because I've forgotten which the order in which you should put outputs and labels in. So if you're always confused, look up the documentation of which order you should put it in. But in PyTorch, it's outputs and then labels. And then we lost that backward. We spent a lot of time last time talking about this. Does anyone remember what's happening here with lost that backward?
Calculus.
Calculus, basically. Back propagation, right? So it basically says, all right, where does this loss come from? Okay, went through this criterion. We can do some calculation of what the gradients of that is. And okay, it went from outputs. Okay, let's go to outputs. It goes to model. That's where our gradients should go. The model, right? Because so it does the computation of gradients. So computes the gradients and stores it in the model parameters dot grad attribute. This is backprop or auto diff. Auto diff as an automatic differentiation. It's a very specific type of backprop where the computer does it for you, basically. That's all it is. Okay, so and we do optimizer dot step. Does anyone know what's happening here with optimizer dot step? Yes.
Step it's taking like to figure out the optimization.
Yeah, it's actually performing the optimization, right? It loops through your parameters, look at their dot grad attributes for every single parameter with the defined dot grad attribute. That basically means we have computed the gradients for them, gradient descent, or in this case, atom optimization, but it's the same idea. And then we have one more very important thing to write here that also is related to the optimizer. What is it, do you think?
So,
Something.
Zero grad.
Zero grad. That is exactly correct. Can you explain why we need zero grad?
So that we don't accidentally like let the leftover gradients from this step affect the next step.
That is exactly correct. That it's a very small implementation detail in loss.backward where instead of just calculating the gradients and storing it in the dot grad attributes, it's actually adding it to the dot grad attributes. And the reason why we do this is because sometimes we have multiple losses and it just makes things slightly easier. But we want to be very careful with actually putting in the optimizer.zero grad because it basically looks through all the parameters and zeros their dot grad attribute. Because if we don't do that, if you imagine, the dot grad attribute just keeps getting added to and it gets bigger and bigger and bigger and bigger, and you just get not a number in the end. And we don't want that. So optimizer.zero grad. And we have a little bit like end of epoch loss, right? And it's actually not just loss.item. We actually want loss.detach .cpu .numpy. And you're wondering what the hell is happening here. Loss.detach. Well, all that does is it just says, because our loss function currently here, or our loss value, has this whole like computation graph attached to it, right? Because it's able to, has to compute the gradients. We first detach to basically say, all right, let's get rid of that thing. Because all we want is the actual value of the loss. Now CPU puts it from the GPU back to the CPU, and then .numpy changes it into like a normal number that looks pretty when we print it. So hopefully okay. Okay, cool. That was a siren sound for those who was watching the recording. Very, very faint one, but it's there. And yeah, you can't just do .numpy directly because they'll be like, oh, it's the GPU. We can't just do a .numpy. So you have to do the .cpu. Yes.
I actually ran with the item parentheses, and it does give me some sort of a float number.
Oh, okay. Honestly, that probably works. I just do this just to be sure. I think item probably works. I think it's probably actually like TensorFlow that has more issues with this, but I like to do that just because. But you don't have to. The item is just this, by the way. I believe this also just works. I like to do this because why not? Okay, I'm gonna run that, and we do a very similar thing with test, right? So if you remember, what we want to do with test is we want to actually just iterate through the entire train logger. Well, the first thing we do is model.eval, right? Does it make sense why we're doing model.eval? Okay. So again, model.eval is just make sure we're in the evaluation mode. It stops trying to calculate running means and variances for batch normalization that actually uses the existing ones. So for I batch in TVDM, because I also kind of want to see the progress of it. Enumerate test loader actually. And then we want to, oh, that's weird. Why are we only indenting by 2 this time? It's fine. I'll just do it manually. Inputs, labels, equals to batch. Again, just a normal thing. Remember, our model is still on the GPU, so we got to do inputs equals to inputs.to device. And labels equals to labels.to device. And then we have our outputs, which we pass through the model. And we have our loss function. Actually, we're not even calculating the loss function anymore in this case because we want the accuracy, right? So you remember what we talked about with argmax outputs, the argmax. Have we talked about argmax? I think we have. Have we?
I think we did briefly.
We did briefly. So basically all it says is it just looks at your output vector and basically says, okay, which entry is the highest one? And that's going to be your prediction, right? So it just says which entry is the highest one, give me that the actual number of that entry, and then with that entry, we actually know what our output prediction is, and we're able to compare with the labels to say, is this actually correct? So axis equals 1 because the dimension is batch times 10, right? And we want to do argmax on the actual on the 10 dimension. Is that so? Hence the axis equals 1. I think it's dim actually. Dim equals 1. I think axis and dim both work in PyTorch, but I'm actually going to call this predictions. That's actually what it is. You want? Oh, whoops! Accidentally read it, but we need to correct plus equal. We're trying to count the number of correct outputs that we have done. Predictions equals labels, right? So basically, it just does like a pairwise comparison of like, does our predictions match what the label actually is? And we can do a dot sum because remember, true is 1, false is 0, right? So if you just do a dot sum, it basically counts the number of correct entries we have. And then we can do a dot item, to basically turn it back into numpy. But I'm going to do the fancy little detach stuff because I like doing this. Dot detach dot CPU dot numpy. Go. And remember, accuracy is the number of correct predictions to the number of total predictions we have made, right? So equal accuracy, we do 100 times correct divided by the length of the test data set. This is one way you can write, and a percent like that. And then visualize the performance. I'm going to do inputs like that. And then we can visualize the current model's performance by basically saying, let's look at some example outputs and see does the model guess this correctly. So that's just what this bit of code means. Does it make sense what's happening here? Okay. One fun fact, something in Python that I really like using is something called f-strings. So basically for f-strings, you can do something like, end of variable, right? And it will basically just print out variable in that. So what you can actually do is something like end of epoch accuracy and just straight up do that. And then whatever you put inside here, it can be expressions or whatnot, it will just be printed out, right? It's a new thing, I believe, in Python 3, which is why not a lot of people, like who are older programmers, who have been using Python since Python 2 actually likes doing this. They like to do some weird string formatting thing. But I think this is kind of elegant, so I'm going to keep it here. Yeah. Okay. Just get rid of that. Okay. Now, with that in mind, let's run this thing. I honestly don't know how this will do. It may give me an error. I think it's going to give me an
Can you
error.
scroll up a little bit?
Oh yeah, 1 second. Oh, it's actually working. There we go. Okay. Where?
To the testing.
Testing. There we go. Here. And if you're wondering what this is, it basically just translates our actual prediction outputs to what the corresponding class is, which it just allows us to better print the predictions. Let's see how the models do it. Oh, oops. NumPy array does my bad. I guess I should have done the item. Which actually converts it because we're actually in the NumPy mode, but we actually want it to be in PyTorch. That's my bad. So do the item. Ignore what I said about everything there. That is my bad. Because he actually trains decently fast, 50 something iterations per second. It's not bad. So you see at the end of the epoch, the loss is 0.99. The accuracy is 66%. That's not bad. It's not bad at all, right? It thinks this is a deer, but it guesses that this is a deer, but this is actually a plane. Because that's like a side of the plane. So I can see why it messed things up like that. But yeah, truck, ship, car, deer. So the accuracy is not bad, but it's starting to increase. But we can see that happen. With the 30 epoch, we're already back up 71%. Are we only looking at the ball? No, we're not. Actually, we just happen to be getting really unlucky. But there we go. See, it labeled as deer correctly. That's pretty good. I wouldn't be able to tell that's deer. I would be actually. when you have perception issues, let a machine do it for you. Basically, like it's able to actually, you know, like dog playing that, but like it's able to actually, you know, guess some things pretty closely. And one of the things that you may actually notice is that we're using the very last inputs. The very last inputs sometimes can be a little bit dodgy because yeah. So but you can actually see it working, right? We have an accuracy of 69%, 71%. That's not bad for CIFAR-10. You might be like, okay, it's not up to human performance, right? Like it seems like it could be better, right? Like because we can probably recognize this at like 95% of the time. And here's the reason why I'm giving you CIFAR-10 instead of MNIST. If you remember, MNIST is a handwritten digit data set. CIFAR-10 is actually a decently difficult problem. Like if you just try it out with like normal fully connected networks, you get like 60%. If you try it with CNNs, like some simple CNNs like this, you get like 75%. With MNIST, you can get to like 95, 99% decently easily if you just have a CNN network, and I think that's not as fun. CIFAR-10, despite the fact that today, if you look at a leaderboard for CIFAR-10 classification, people have gotten to like basically perfect accuracy. Like we go, let's see, CIFAR-10 accuracy. I believe there's like, yeah, there we go. With code, they do these sort of like benchmark things. You can see like the most recent one, the best one has like 99.5% accuracy. But that model is also 632 million parameters. If you want to know how many parameters our model has, we can. In fact, at the very end, let's see, what's our very 69%. Nice. So that was totally planned, by the way. But if you want to count the number of parameters our model actually has, it's not that bad. You do size equals 0. Import numpy. You can import numpy. Okay. So if you want to actually see how many parameters your model has, you just loop through all the parameters in the model and basically do size plus equals np.prod param.shape. So if you think about what this is actually doing, if a parameter is like 64 by 32 by 32 by 32, and what's actually happening is the total number of parameters in that is 64 times 32 times 32 times 32, right? So that's why we do np.prod, which basically multiplies everything together. You can print at the very end, you know, number, all parameters, parameters, and spell, size. So we do that, go back, you'll see our model has 189,000 parameters. It's not big. It seems very large, but honestly for CNNs, that's not bad. Remember that this one's 632 million. That's a lot. But yeah. So that's what I'm getting at. All right. At the very, very end, let's try to save the weights. And basically just yeah, let's just try to save the weights. Saving the weights is very helpful, especially since we're training much bigger models. A lot of things you don't want to retrain things every time. Like this one trained pretty fast, but the way to do it is just model. State model state dict. And what state dict is basically a dictionary of all the model parameters and its current state. And the way that differs is model.parameters, it only gives you pretty much the trainable parameters. Like it doesn't give you like the running mean that batch normalizations actually has. But if you do state dict, it actually saves everything, right? And we can save it as like, you know, in a folder called just, you know, model.pt. You don't have a name of PTH. PTH is just kind of like convention or PT or PyTorch weights. You don't have to. Let's save it just like that. Yeah, that's saved. And if you want to reload the model, let's call it model new. The way you do it is you initialize a new CNN and you do new model. Let me see. Yeah. Okay. You basically do new model new load state dict forge.load, because it takes in a state dict, and to be able to retrieve that state dict, you need to do model PDH, because PDH. So that's what we saved it as. I'm going to put the model back to the device, and as a sanity check, what we can do, you see, just to make sure. That's very long. Okay. We can test the model to make sure it has the desired accuracy. So test the model. Oh, before we test the model, actually, it does it for us because it does the model.eval. But sometimes you want to do a model.eval here just to make sure you're not trying to train your model any further. Unless that's actually what you want to do. So test model, or just test event? Okay. Test model, test loader. I think that's all we need. Is that all we need? No, device, right? Device. There we go. She goes through everything, and it says our model has 69.27% accuracy, exactly as what we had here at the very, very end. So we have successfully just loaded the weights. Now, as I mentioned before, if you were to just say, okay, I finished training, I am going to just save the model away for use later, then you just save the model. However, if you're planning to resume training from this very point, sometimes you also want to save the state dict of your optimizer, and it will be the same exactly you would do it. You would do something like here. You torch.save instead of model.state dict, you would do in this case optimizer.state dict, and then you will load it the exact same way. Sometimes you want to do that because remember, your atom optimizer is keeping a running mean of all your weights. Keeping a running mean of all your gradients, right? If you want to reinitialize and train from this exact point, it has to remember what those running means and variances are. So in order to do that, you have to also save the state dict for the for that thing. So yeah. Any questions? 1 second, while I'm at it. 2 seconds. So with that, any final questions before we go?
Thank you.
Yes.
Change the detached back to item. Can
Yeah.
you delete CPU and NumPy?
Yes, I just deleted everything. I only left item.
And the-
Yes, could you just show the code?
Yeah. I'll show the code. My bad. Over here.
It's test.sum.
My bad for all the CPU.detached thing. That's just what I'm used to, but I forgot that there's that item you need to use. Yes.
I'm getting the same non-type problem. Could you show the dimensions of the neural network again?
Sure. So here. So you want to make sure that we don't have a strike here, and everything here should match. You're getting that mat1 and mat2 doesn't multiply issue.
I get that if I change the parameters around, but as of now, I'm just getting it saying it's non-type.
It's num type. Did you return X at the very end?
Oh, right. Okay.
There you go. Yeah. Any questions?
Could you like briefly tell us again about the batch norm? What does batch
Oh,
norm do?
Like how it works. Basically, all this is just says across the batch, we look at every single feature map because we have like a bunch of feature maps at every single hidden layer, right? For every single feature map, we look at that feature map across the entire batch of, let's say in this case, 128 128 images. And basically say for that feature map, let's normalize that feature map so that it has across the entire batch a mean of 0 and a variance of 1.
So
That's what batch normalization does. It normalizes across the batch. So if one of the values in this batch has a really, really high value, you'll bring down every single other value in your after the batch norm as well. But we're kind of assuming that because we have a 128 as batch size, if your batch size is big enough, it will like average everything out and it will be able to successfully normalize the hidden outputs of every single one of these. Does that make sense? Okay. Any final questions before we go?
quarter.
All right. Thank you. You have just completed advanced track. That's amazing. You basically showed up consistently for 6 weeks, and I think that's a really great feat. Next step will be projects. We haven't sent out the projects link to apply yet. If you have done advanced track, you're going to get into projects. But just keep an eye on the Discord, and we will be sending out the sign up link for projects pretty soon, hopefully. Again, here's a feedback form. Again, like I'd rather do a shortened version of things. So if you really want to give us feedback, you can go all the way up to basically where the cluster is, and in there you'll be able to find the presentation and give us feedback that way. But yeah, thank you so much for the quarter, and thank you for coming to Advanced Track.
Yeah.